You know, when you or I make a mistake, we feel it, we think about it, and we try something different next time. But have you ever stopped to wonder how a piece of software does that? How does a machine, with no feelings and no intuition, actually learn from its errors? Well, today, we're going to pull back the curtain and take a journey into the machine's mind to see how AI really learns.
So here's our roadmap. First, we'll get a handle on what machine learning actually is. Then we'll see how an AI figures out it messed up and starts correcting itself. We're going to follow its path to find the best answer, look at the roadblocks that trip it up, explore the seriously smart tools it uses to get around them, and we'll finish up with the ultimate balancing act that every AI has to master to be truly intelligent. Okay, so at its core, you can think of a neural network as this giant machine with millions, sometimes even billions, of tiny little digital knobs. In the biz, we call these parameters or weights. And the whole game is to tune every single one of those knobs just perfectly to solve a problem.
Which, of course, brings us to the biggest question of all. With all those millions of knobs, how on earth does a network find the one perfect combination that lets it look at a brand new photo and confidently say, yep, that's a cat? It's not just random guessing, believe me. There's a really powerful process going on under the hood. The real secret sauce to AI learning is this incredibly clever process for figuring out who's to blame for a mistake. It's called backpropagation, and it is the engine that drives pretty much all of modern AI. When the network gets an answer wrong, backpropagation literally works backward to figure out which of those little knobs were most responsible for the error, so it knows exactly what to fix. Let's see how it works.
Right, so every student needs a teacher, and for an AI, that teacher is something called the loss function. Imagine the network guesses, okay, I'm about 30% sure this picture is a cat. The loss function compares that to the right answer, which is this is 100% a cat, and then it spits out a single number, just one score that tells the network exactly how wrong it was. And once it has that score, the goal becomes incredibly simple. Get that number as low as you possibly can. That's it. The entire training process is just one massive, relentless hunt for the one perfect setting of all those millions of knobs that gives it the lowest possible error score.
This hunt happens in a loop that just goes over and over and over. First, the data flows forward through the network and it makes a guess. Second, the loss function calculates that error score. Third, and this is the magic step, that error score is sent backward through the entire network. That's backpropagation. As that error signal flows back, it tells every single node how much it contributed to the mistake. And fourth, based on that feedback, each knob gets turned just a tiny bit to make the next guess better. Then the whole cycle repeats, millions of times. But hang on, how does the network know which way to turn those knobs? I mean, randomly twisting millions of them would take forever, right? It needs a guide, some kind of map to find the lowest point of error. And this is where a truly brilliant algorithm called gradient descent comes into play.
I love this analogy because it just clicks. The mountain is this huge invisible landscape of all possible errors. Our AI is the hiker, and it's lost in a thick fog. It can't see the whole map, not at all, but it can feel the ground right under its feet. So to get to the valley at the bottom, all it has to do is find the steepest downhill direction and take a step.
And that's exactly what gradient descent is. It's the mathematical tool that calculates the slope of that error mountain at any given point. It acts like a compass that's always pointing in the steepest downhill direction, telling the network precisely how to adjust all its knobs to lower that error score. So how big of a step should our hiker take? Well, that's controlled by something called the learning rate. If you set it too high, it's like taking these giant, reckless leaps down the mountain. You could completely overshoot the valley and just end up bouncing back and forth between the ridges. But if you set it too low, it's like taking tiny, shuffling baby steps. Sure, you'll get there eventually, but it could take an unbelievably long time. Finding that just right learning rate is a real art.
Now, this all sounds pretty good in theory, doesn't it? But there's a huge catch. The error landscape for a real neural network isn't a nice, simple bowl. It's actually this incredibly complex, treacherous terrain that is full of traps that can stop our learning algorithm dead in its tracks.
And here are the main villains our hiker has to deal with. First, you've got local minima. These are sneaky little valleys that feel like the bottom, but they're not the true lowest point on the whole map. Our hiker gets stuck, thinking its job is done. Then you have saddle points. These are really tricky flat areas that slope down in one direction but up in another, totally confusing the hiker. And maybe worst of all is the vanishing gradient, where the ground just becomes so flat that our hiker can't feel any slope at all and just stops moving. Learning is over.
And this chart shows that vanishing gradient problem perfectly. It's showing the learning speed for different layers in the network. Just look at those bottom lines. Those are the earliest layers in the AI. After just a few rounds of training, their learning speed completely flatlines. The feedback signal that's being sent backward is basically fading to nothing by the time it reaches them. So these crucial early layers are just frozen, unable to learn anything new. The network is paralyzed.
So if the landscape is so dangerous, how did AI ever get so powerful? Well, this is where human ingenuity comes in. Researchers developed a whole toolkit of clever breakthroughs that basically gave our hiker a much better map and some high-tech hiking gear to navigate this terrain.
One of the biggest game changers was just adding a little bit of chaos. Instead of having the hiker look at the entire map before every single step, which is slow and gets stuck easily, we can use something called stochastic gradient descent, or SGD. With SGD, our hiker just takes a quick random glance at a tiny piece of the map and takes a step. The path becomes noisy and kind of jerky, but that randomness is the key. It's what can jolt the hiker right out of those tricky local minima and saddle points. Another massive innovation was changing the guts of the neuron itself. For decades, networks used this S-shaped curve you see on the left, called a sigmoid. But look at the ends. They're almost perfectly flat. A flat line means the slope is zero, which means learning dies. This was a huge cause of the vanishing gradient problem. The modern solution, on the right, is the ReLU function. It's so much simpler. If the input is negative, the output is zero. If it's positive, you just get a straight line with a constant slope. That simple change keeps the gradient from disappearing and lets us train much, much deeper networks. It was a total game changer.
Okay, we've seen how AIs learn and how they overcome obstacles, but there's one final, huge challenge that really defines all of machine learning. And it's not about finding a perfect answer. It's about striking a very, very delicate balance.
This is called the bias-variance trade-off, and it's the central tug-of-war in this whole field. Bias is when your model is too simple. It just can't capture the true patterns in the data. Variance, on the other hand, is when your model is too complex. It starts learning all the random noise in your training data and can't generalize to anything new. The goal is to find that perfect sweet spot, right in the middle.
So a model with high bias is what we call underfitting. Think about it like this. You've got data that clearly follows a curve, but you try to describe it with a perfectly straight line. Your model is just too simple. It's going to be wrong on the data you trained it on, and it's going to be just as wrong on any new data you show it. It just fails everywhere.
Now, on the flip side, a model with high variance is overfitting. This model is way too complex. It doesn't just learn the pattern, it basically memorizes every single data point you showed it, including all the random, meaningless noise. It's like tracing your data with a ridiculously squiggly line. It'll look absolutely perfect on your training data, but the second you show it something new, it will fail spectacularly.
And this really brings us to the final, most important idea. In the real world, data is messy, it's noisy, it's unpredictable. So the ultimate goal for AI isn't perfection on the data it's already seen. The true North Star is generalization, the ability to perform well on the messy new data of the future. It's this constant dance between being too simple and too complex and finding that perfect balance. Well, that's the real art of making machines that can truly learn.